Okay, today's lesson is on M2I2ACID, which is an acronym. M2 is for maximums and minimums. I2 is for intercepts and inflection points, which is points of inflection, POI. A is for asymptotes. C is for curvature. I is for increasing, and D is for decreasing. Now, basically, the M2I2ACID acronym is a way of, say you're given a function, y equals or f of x equals whatever equation, you go through and find each of the items that we have listed here. Where are the maximums? Where are the minimums? Where are the intercepts? That includes both x and y intercepts. Where are the points of inflection? Where are the asymptotes? What kind of curvature does the graph have and where? Where's the function increasing? Where's the function decreasing? You go through and you spell all of this stuff out based on the methods we've already learned, and you can graph the function using all this information. So it's like giving a complete analysis of a curve. All of its important features are then pointed out when you go through this process. So it's somewhat lengthy to do this for a function because there's so many things to find, but these are all things that you have already found, and there really isn't anything new to today's lesson other than just summing all of this information up on a particular function. So this is a good preparation for college level calculus, where you're looking at an in-depth graphical analysis of a function. So having said that, we're going to go ahead and do two examples where we fully discuss M2I2ACID for each. Now, when I say discuss it, I'm not talking about writing a paragraph or getting up and giving a speech about it. The discussion is more just calculating these values and listing them out, and then finally ending with a graph of that function. Alright, so here's our first example. We're going to use y equals 2x minus 6 over 4 minus x. So you can probably notice this is a rational function. Different functions have different features from things you've learned in years past. Step 1 in doing M2I2ACID is to find the first derivative. We will look at the first derivative and when is it undefined, if ever, and when is it equal to 0, if ever. Those are going to give us our critical values. Okay, so basically find the first derivative and the critical values for the function. So since this is rational, we're going to have to use the quotient rule to find the derivative, which is bottom times the derivative of the top minus top times the derivative of the bottom, all divided by the bottom squared, or low d high minus high d low over low low, however you would like to remember it. So we're going to start with the bottom, denominator 4 minus x, times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom quantity squared. So this is going to equal 8 minus 2x minus, if I distribute this 1 in, negative 1 in, sorry, negative 2x plus 6, all divided by 4 minus x squared. I'm not going to multiply that out. Y prime is equal to 8 minus 2x plus 2x minus 6 all over 4 minus x squared. Oops, square outside the parentheses. And so this is 2 over 4 minus x squared. So, if I set this equal to 0, say I cross multiply here, you get 2 equals 0, which is a false statement. So the first derivative here is not ever going to be equal to 0, but it is undefined when x equals 4. That's going to cause the denominator to equal 0. So that is a critical value for this function. Alright, yes, I see you, kitty. Now we're going to find the second derivative for step 2. So in order to find the second derivative, I might want to think of the first derivative as 2 times 4 minus x to the negative 2 power. That's going to be an easier way to differentiate that function using the chain rule. So we're going to go on to step 2. Oops. Step 2, find the second derivative, and then when does it equal, oops, that's very messy, if ever, when does it equal 0 if ever, and when is it undefined if ever. Okay, so the first derivative from the last page we said was 2 times 4 minus x to the negative 2 power. So to get the second derivative, I'm going to use the chain rule, take the derivative of the outside function, which means I'll have a negative 4 here, copy the inside function, subtract 1 from the power, and multiply by the derivative of the inside function, which is negative 1. So this is going to be negative 4 times negative 1 is positive 4 over 4 minus x to the third power. Now, if I set this equal to 0 and cross multiply here, I get 0 equals 4, which is a false statement. It's never going to be equal to 0, but it is undefined when x equals 4, the same as the first derivative. So that's going to be the point that we're going to want to look at very closely. Okay, so we've taken care of step 1, find the first derivative and the critical values associated with it. Step 2, find the second derivative, where is it equal to 0, when is it undefined. Now, step 3, we're going to make a sign chart. And basically, what we're going to do is we're going to analyze the signs of the first derivative, and, oops, I am starting with function notation and switching to y notation. It obviously doesn't matter, but I like it to be consistent. Okay, so signs of the first and second derivative. Basically, along the top, you want to put x values that are critical values that you found from setting the first derivative equal to 0 or finding when it's undefined. So we got 4. And also any values that you get for x when the second derivative is set equal to 0 or undefined, which we got only one, the same one. You might have a lot more numbers than this, and but for this one we only have 4. And you want to also include numbers between and beyond these. So I'm going to go negative infinity and positive infinity. And obviously I'm not going to plug those exact numbers in. I'm just going to probably pick a number smaller than 4 like 3 and pick a number larger than 4 like 5 and use those instead. So what I do now is I say, okay, what is f prime of 3? Because I already know that the first derivative and the second derivative are both undefined at x equals 4. So f prime of 3 would be, and again, 2 over 4 minus x squared was our first derivative. So this will be 2 over 4 minus 3 squared, which is 2 over 1 squared, which is just 2. And so that's a positive. We don't really care about the value, we just care positive, negative. Now, f prime of 5 is equal to 2 over 4 minus 5 squared. So that's 2 over negative 1 quantity squared, which is again 2. So this is positive on the other side also. Now we're going to do f double prime of 3, and f double prime was 4 over 4 minus 3 cubed. Well, 4 minus x, but I'm plugging in the 3 there. So this is going to be 4 over 1 cubed, which is 4. So that's positive. And then f double prime of 5 is equal to 4 over 5, erase, 4 minus 5 cubed, which is 4 over negative 1 cubed, which is negative 4, so this one is negative. Okay, I hope you've been writing this down, because we're going to have to reflect on all of the information we've gathered so far in order to do our discussion for the M2I2 acid for this function. So, M2, that's our maximums and our minimums. Now, how do we know if we have maximums and minimums? Well, the first derivative has to change signs. If you look at the sign chart, our first derivative is positive, then undefined, then positive again. It never changes to negative. So there are no maximums and minimums on this function. Now, I2, intercepts and inflection points. Okay, intercepts we find by taking our original function, y equals 2x minus 6 over 4 minus x, and we're going to sub in zeros for the x's to find the y-intercept. So 2 times 0 minus 6 over 4 minus 0 equals negative 6/4, which simplifies to negative 3/2. So I have an intercept at the point, and this is a point, I write it as a coordinate pair, 0, negative 3/2. Okay, that's my y-intercept. Plug 0 for x. Now, for the x-intercepts, I put a 0 for y. So if I cross multiply here, basically that's the same thing as saying 0 equals 2x minus 6. Add 6 to both sides, 6 equals 2x, divide by 2 on both sides, 3 equals x. So I have an x-intercept at the point 3 for x, 0 for y. X-intercept. Sometimes those x-intercepts are a little bit more difficult to find. Sometimes you end up having to use quadratic formula, or sometimes they're irrational. You'll just use the same kinds of methods you used in Algebra 2 to find those. Now, points of inflection occur when the second derivative changes signs, and so Second derivative goes from positive to negative at x equals 4, but x equals 4 is not a defined point for the function itself. The function never equals 4. So there are no points of inflection. It would have to actually be a point on the graph. Like when you find that x value, plug it into the original equation to find the y associated with it and end up with a point on the function. There is no point of inflection at all. Now, for the asymptotes, A is for asymptotes, using the same things that you learned about in Algebra 2, to find the vertical asymptotes, you're going to set the denominator equal to 0, and you should have a half sheet of notes that you got during our limits unit that has a summary of rational functions with all the asymptote rules, so please refer to that if you've forgotten. So 4 equals x is your vertical asymptote. Horizontal asymptote, you look at the degree of the numerator and the degree of the denominator. In this case, the degree of the numerator is 1, it's just x to the first, and the degree of the denominator is also 1. So that means that it's going to be y equals the ratio of the leading coefficient of the numerator, which is 2, and the leading over the leading coefficient of the denominator, which is -1. 2 divided by -1 is -2. So y, y equals -2 is your horizontal asymptote. And C is for curvature. So, curvature. When is this function concave up? Well, that's going to be when the second derivative is positive. The second derivative was positive from -infinity to 4, and negative from 4 to infinity. So concave up, -infinity to 4, and concave down, 4 to infinity. Okay, then the next is the I and the D, which kind of go together. I is for increasing. When is the function increasing? Whenever the first derivative is positive. The first derivative is positive everywhere except for 4. At 4 it's undefined. Sorry for flipping back and forth so much. -infinity to 4, and then also from 4 to infinity, not including 4. When is it decreasing? Well, that's when the first derivative is negative, which is never on this particular function. So, after you've done all of that, you can use this information to make a graph of your function. You do want to be able to do this by hand. Let me see, I think I can make this into graph paper. Yes. Okay, so when you do this by hand, you're going to plot all the information that we've gotten. We know that we have I like to put the asymptotes down first. Vertical asymptote at x equals 4. And a horizontal asymptote at y equals -2. Okay, I want to put my intercepts on there. 0, -3/2. So 0, -1.5. There's my y-intercept. My x-intercept is at 3, 0. So there's my two intercepts. I don't have maximums, I don't have minimums, I don't have points of inflection. So really this is all I'm going to need to make my graph. If you want to generate a table of values to get more accurate points, that's fine, but the most important thing is that you're including all the information from your M2I2 acid. So our curvature says we're concave up from -infinity to 4. So I should see this function looking kind of bowl-shaped. It's a little weird on a rational function, but there's our concave up, and our concave down is from 4 to infinity. Also, this function is increasing on its entire domain, so I should see it going up from left to right on both branches of this graph. And there we have it. The graph is done. Okay, so second example. I may not have time to do the whole graph on this one, but I'll let you finish that one on your own. Switch back to regular paper. Okay, here's our function. Y equals, this is example 2 and our last example, 1/3 x cubed minus x squared minus 3x plus 5. So, first derivative, x squared minus 2x minus 3. Set that equal to 0 to solve for the critical values. 3, 1, minus, plus. Okay, so now I set each of these factors equal to 0. X equals 3 or x equals -1. Those are my critical values, and it's never undefined. Now I'm going to do my second derivative. So the derivative of the first derivative function, 2x minus 2. Set that equal to 0, and it is factorable. Now if you set 2 equal to 0, it does not equal to 0, so that does not produce a 0 of the second derivative, but x minus 1 equals 0 gives you x equals 1. So this is going to be the x-coordinate of the point of inflection. These are our critical values. All three of these values are going to go in our sign chart. So we'll have f prime of x, f double prime of x, and then the x values. I'm going to put them in order from least to greatest, leaving spaces in between them. -1 was our smallest critical number. 1 was the x-coordinate of the point of inflection, and then 3 was the other critical number. Now, I'm going to choose numbers between and beyond, so -infinity will go here, which I might want to use like -2 to represent that. Between -1 and 1 would be 0. Between 1 and 3 would be 2. And then I want infinity on the other side, I'll use 4 to represent that. So I can go ahead and fill in where my zeros were. Okay, at -1, this was a 0 for the first derivative. At 3, this was a 0 for the first derivative. And at 1, this was a 0 for the second derivative. Now I'm going to determine the signs of the first derivative and the second derivative for each of the holes in my chart. So f prime of x is equal to, where was that function? X squared minus 2x minus 3. So I'm going to plug in a -2 for that. F prime of -2. And that's going to give me a positive. So I fill that in. Now I want f prime of 0, which is a negative. Now I'm going to plug in 1. Which is also a negative. Plug in 2. Which is also a negative. And last, I'm going to plug in 4. Which is a positive. Okay? Now I'm going to do the same thing with my second derivative. F double prime of -2. This is going to be, it was 2x minus 2, so 2 times -2 minus 2. So that's going to give me a negative. F double prime of -1 that's also negative. F double prime of 0, negative. And then F double prime of 2, that's a positive. And F double prime of 3, let me go back over here on this side and erase so I have a little bit more room. That's a positive. And F double prime of 4 is also a positive. So my sign chart is complete. Now I can go through and do my analysis of each of the features. M2, maxes and minimums. Remember, maxes and minimums are where we change signs on our first derivative. So I have a potential candidate for that at x equals -1 and at x equals 3. But I don't just want the x values, I want the y's associated with those. So I'm going to plug those into my original function. 1/3 times -1 cubed minus -1 squared minus 3 times -1 plus 5. So this is going to be, -1/3 minus 1 plus 3 plus 5, which is going to give me 8 minus 1 is 7, minus 1 is, minus 1/3 is 6 2/3. So, -1, comma, 6 2/3. Now, can you tell me, is this a maximum or a minimum? Well, let's look back at our sign chart. Whoops, too far. Sorry. Alright, at -1, it goes from positive to negative, increasing to decreasing. That's a maximum. Okay, what about the minimum? The minimum is at 3 because it goes decreasing to increasing. So we have a minimum when x equals 3. We just need the y that goes with it. And that's going to be 9 minus 9 minus 9 plus 5, which is -4. So the minimum is going to be at 3, -4. Alright, y-intercept. If I plug a 0 into the original function for the x's, I get 5. So I have the point 0 for x, 5 for y. That's my y-intercept. Now, the x-intercepts on this one, let's go ahead and use a calculator. Hopefully you remember how to do that. Put your function in y equals, go to the second calculate menu, and then find the zeros. So you're going to have 3 of them. I'm just going to write them down because you can't see me punching buttons in the calculator. Make sure you can get these. Uh-oh, it's warning me I have 1 minute left. I have a time limit on these things. 30 minutes is all I'm allowed to do. Alright, points of inflection. We have the x-coordinate of 1. We plug that into the original function to get the y-coordinate of 1 1/3. And I'm going to go ahead and write the rest of the answers, and you hopefully can figure this out. Concave up is from 1 to infinity. Concave down is from -infinity to 1. Increasing is from -infinity to -1 and 3 to infinity. And decreasing is from -1 to 3. Good luck on your 4 problems that you do M2I2 acid for homework.